네, 지금부터 2021년 데이터경제와 혁신 세미나를 시작하도록 하겠습니다. 안녕하십니까. 저는 오늘 행사의 사회를 맡은 KDI국제정책대학원의 최하나입니다. 우선 바쁘신 중에도 저희 행사에 참석해 주신 모든 분들께 감사의 말씀 드립니다. 행사를 앞두고 갑작스럽게 코로나가 심해지면서 현장에는 많은 분들을 모시지는 못했는데요. 그래도 오늘 세미나는 작년에 이어서 다양한 분야의 전문가분들을 모시고 풍성하게 준비했으니까요. 많은 시청 부탁드리고 토론에 적극적으로 임해주시면 감사하겠습니다. 오늘 세미나는 KDI 국제정책대학원의 조만 교수님의 개회사를 시작으로 준비되어 있습니다. 그럼 지체 없이 바로 조만 교수님을 모시고 시작해 보도록 하겠습니다.
예, 안녕하십니까. KDI 대학원 조만입니다. 제가 아주 짧게 개회사를 할 텐데요. 그 전에 지금 키노트 스피커 두 분이 들어와 있습니다. 온라인으로. 그래서 제가 이 짧게 영어로 이분들한테 먼저 인사를 드리고 이 개회사를 진행하도록 하겠습니다. I'd like to welcome and appreciate to Professor Scott Stern and Professor Benjamin Jones for the keynote speakers. We very much look forward to talking to you, and I like to excuse for my delivering my opening remark in Korean. Okay? 예, 그러면 오늘 그 제2회 데이터 경제와 혁신 주제로 저희가 다부문 간의 세미나를 준비를 했고요. 작년 요맘때 이 의료, 금융, 부동산 이렇게 세 개의 부문의 데이터 경제를 어떻게 개념화하고 어떻게 추진할 것인가 하는 주제로 세미나를 했고요. 올해는 이제 이 중소중견 기업까지 좀 더 알차게 저희가 준비를 해서 세미나를 열게 됐습니다. 그래서 저 참여하시는 모든 분들이 그 유익한 시간이 되시기 바라고요. 그 이번 작년에도 그랬고 올해도 이 서강대학교 문성욱 교수님이 뭐 세미나에 한 7월 8화를 준비를 하셨습니다. 그래서 문성욱 교수님이 안 계셨으면 이번 세미나가 이 성사되지 않았을 거다 하는 말씀을 드리고요. 마지막으로 그 KDI 대학원의 연구협력처 김현주 팀장님 그리고 최하나 전문원 이번 세미나를 위해서 너무 수고를 많이 하셨고요. 그래서 감사드린다는 말씀 드립니다. 그 오늘 5시 이후까지 저희가 세미나가 준비되어 있는데 참여하는 모든 분들 유익한 시간 되시기 바랍니다. 감사합니다.
네, 따뜻한 말씀 감사드립니다. 다음 순서로는 KDI 국제정책대학원 김준경 교수님의 축사가 준비되어 있습니다. 교수님 준비되시면 언제든지 시작 부탁드립니다.
네, 안녕하십니까. 네, KDI 대학원의 김준경입니다. 오늘 그 바쁘신 중에도 데이터 경제와 혁신 세미나에 참석해 주신 이 발표자와 토론자, 특히 외국에서 닥터 스캇 스턴 씨하고 그 벤 존스 교수님 이렇게 참석해 주셔서 아주 깊이 감사 말씀드립니다. 또한 그 이 세미나를 조직해 주신 KDI 대학원의 조만 교수님 그리고 서강대학교의 그 문성욱 교수님께도 감사 말씀드립니다. 최근 그 경제 환경이 급변하고 있습니다. 한편으로는 한 번도 경험하지 못한 이 세계적인 코로나 감염병 위기가 발생한 지 벌써 2년이 지났음에도 아직 위기 극복의 실마리가 보이지 않고 있습니다. 다른 한편으로는 이 정보통신기술과 기존 산업이 융합되는 4차 산업혁명이 진행되면서 그 빅데이터와 AI 등 디지털 기술이 상품 서비스의 생산, 유통, 소비 등 밸류 체인 전반에 접목됨에 따라서 새로운 성장 동력이 태동되고 있습니다. 또한 코로나 위기는 소비 패러다임의 온라인 대전환을 촉발하고 있습니다. 디지털 전환 시대의 산업정책의 핵심은 기술 진보와 미래 산업 발전에 대한 방향성 제시와 함께 그리고 이해 당사자 자들과의 합리적 소통을 통해서 사회의 혁신 수용성을 높이는 것이라고 생각합니다. 미국과 중국, 영국, 일본, EU 등 세계 주요 국가들은 데이터 경제 활성화 전략을 이미 5년 전인 2017년경부터 추진해오고 있습니다. 우리나라에서도 작년부터 디지털 뉴딜 관련 사업들이 진행되고 있으나 이에 추진에 있어서 일부 장애 요인이 노출되고 있습니다. 금년 7월에 발표된 디지털 뉴딜 2.0의 경우 2025년까지 데이터 네트워크 AI, 그 DNA 생태계를 강화하고 SOC 디지털화를 추진하는 등 그런 사업을 계획하고는 있지만 정책의 방향이 명확하지 않고 그리고 부처별로 단기 시범 사업 위주로 일부는 좀 보여주기 식으로 사업이 선정되고 무엇보다도 이 피해 보상의 대원칙도 없다 보니까 사회적 갈등이 해소되지 못하고 신기술이 기반한 혁신 성장이 제 속도를 내지 못하고 있는 것 같습니다. 월드 이코노믹 포럼에 의하면 우리나라 기업이 체감하는 규제 부담이 OECD 평균에 비해서 부담이 높은 동시에 그리고 전 세계 141개국 중 87위로 하위권에 머물고 있습니다. 이러한 그 과잉 규제는 디지털 기술이 근간을 이루는 4차 산업혁명 시대에 필요한 규제 개선 조치를 지연시킴으로써 기술 발전을 법과 제도가 따라가지 못하는 이른바 regulatory lag, 그러니까 이른바 규제 지체 문제를 초래할 것으로 우려됩니다. 4차 산업혁명 시대에 유망산업으로의 재편과 융복합을 효과적으로 지원하기 위해서는 무엇보다도 규제 개혁이 전제되어야 합니다. 규제 개혁 패러다임은 디레귤레이션에서 더 나은 규제, the better regulation과 smart regulation으로의 조속한 변환이 필요합니다. The better regulation은 규제에 매달리는 대신 이 감시, 모니터링과 처벌에 무게를 두고 uncertainty, 불확실성을 받아들이는 것이며 smart regulation은 규제의 양은 낮추고 이 질은 높이는 OECD 방식입니다. 이와 함께 국회의원 입법제도의 개선이 필요합니다. 우리나라에서는 사전적인 품질 관리가 거의 이루어지지 않는 의원 입법 남발과 이에 따른 과잉 규제 문제가 심각한데 이를 시정하기 위해서는 의원 규제 입법에 대하여 사전적으로 규제 역량 평가를 도입하는 그러한 제도적 노력이 필요하다고 생각합니다. 아무쪼록 오늘 데이터 경제와 혁신 세미나를 통해 발표될 연구 결과와 토론 내용이 국민과 정치권에 큰 임팩트를 줌으로써 현재 성장이 멈춰있는 한국 경제를 다시 성장하는 경제로 전환하는 모멘텀이 되기를 기대합니다. 경청해 주셔서 감사합니다.
네, 따뜻한 말씀 감사드립니다. 다음 순서로는 기조연설이 준비되어 있는데요. 오늘 행사를 위해서 먼 미국에서 두 분을 모시게 되었습니다. 기조연설자로 참석해 주시는 교수님들은 서강대학교의 문성욱 교수님께서 소개해 주시겠습니다.
Dear professors, distinguished guests, and online audience, we have first keynote speaker for Data Economic Conference today. It is my honor to introduce Professor Scott Stern, David Sanoff Professor of Management of Technology at MIT Sloan School of Management. Scott explores how innovation and entrepreneurship differ from more traditional economic activities and the consequences of this difference for strategy and public policy, so-called the economics of innovation and entrepreneurship. Specifically, he studies entrepreneurial strategy, innovation-driven entrepreneurial ecosystems, and innovation policies and management. Scott has also worked to bridge gap between academic research and the practice of innovation and entrepreneurship. His creative and integrative framework keeps stimulating scholars and practitioners around the world. Scott did his PhD in economics at Stanford University and spent his early academic career at MIT and Kellogg School of Management, Northwestern University, where I was his student. The title of his speech is the Artificial Intelligence Shift, Implication for Korean Innovation and Strategy. Please give Professor Scott Stone a round of welcome applause. Scott, the floor is yours.
Great. Hold on just 1 second. Thank you so much. I'm delighted to be here. Let me just get myself up here, make sure we get this right. And can you see my screen now? We're doing okay? Great. Look at that. I can even see myself. And can you guys hear me okay? Great. Well, thank you. Thank you to Dr. Kim, to Sung-Wook, to the entire team at KDI. I'm so delighted to be have the opportunity to spend a little bit of time with you talking about this very important shift in, I think, the role of data, the implications that's going to have, the rise of artificial intelligence, and the implications that's going to have for Korean innovation, Korean strategy, and more globally. Before I get started, I also should say that I only wish that I had the opportunity to be there in person with you. It's good seeing some good friends from KDI as well as the broader Korean ecosystem. And so it's great to at least join you on Zoom, and I look forward to an opportunity to join in person. And I also looking forward to hearing from my dear colleague, Ben Jones, in a little while. So today, what I'd like to do to start out this conference is really talk about this really fundamental shift that's going on that you've probably already heard about, but I'm going to try to kind of sharpen what some of its implications are and also sharpen what it might mean for the future of innovation and the role of strategy at both the country level and at the firm level. So by now, everyone who's probably listening here knows that artificial intelligence, machine learning are dramatically transforming the world that we live in already. Whether or not it's the ability of advanced machine learning trained robots to dance, whether or not it's the still elusive but sort of coming online world of autonomous vehicles, or the more general representation of machine learning neural networks across a wide range of decision-making, prediction problems, applied business problems, scientific problems, even characterizing solutions to COVID. All of that is on the table today. Just to give you a sense, though, of I think that it's easy to use the word AI. We don't yet have a artificial intelligence that thinks like a human, that has common sense, but we certainly have machines that are getting ever closer to simulating, in some sense, what we might think of as very human qualities, the ability to kind of mimic, in some sense, our ability to talk around things and the ability to structure things. So let me introduce you to GPT-3, which is a probably the leading or one of the leading text generators in the world. GPT-3 can come and uses a wide variety of text, trains itself on all sorts of information it gathers from the internet, and then it uses that to basically create, well, one of its many uses is to basically create real essays, or create real stories, or create real reports in real time. And so I thought that as a beginning here, I would in fact just input into GPT-3 the very name of this conference, so you know what today's activities will be about. Data Economy Conference, Data Economy and Innovation Cases in the Multi-Sector in Korea. Let us see what GPT-3 came out, once again, with no human intervention besides this input. So let's see what the output is here. Oh, join us in Seoul as we discuss the most important issue of all time, the interconnectivity of technology and data in Korea. and look how it can be integrated into society, industry, education, and the wider world, ... The seminar will be followed by a discussion on blockchain, which is already an important topic. I'm not sure, but this is sort of not bad for something that, right, was self-generated by a machine learning algorithm. And so that kind of crystallizes this kind of very important idea that there's something shifting in our ability to use computers, to use algorithms, to use data, to essentially start to kind of make predictions about how human beings would write up reports, how human beings might sort of kind of think about activities that are in their minds, think about kind of things to do, and maybe even create new things. And so kind of what I wanted to do was really center what, from my own research, as well as kind of immersing myself both with companies, as well as policy, as well as technologists, what is this shift? What is the AI shift? And I think in some sense, my colleagues, Ajay Agarwal, Avi Goldfarb, Josh Gans, in their book Prediction Machines, actually capture what may be the essential thing that is changing in terms of the information technology revolution. And this is a quote from their book. The task that AI makes abundant and inexpensive is prediction. The ability to take information you have and generate information you didn't previously have. So for example, just in GPT-3, I gave it an input and it predicted what would be a reasonable output that such a conference would be about. To be clear, that has long been an elusive goal for artificial intelligence, but for a long time that goal was stymied. However, starting in the late 2000s, and here's Feifei from Stanford, there seemed to be a sizable shift in using machine learning, and in particular what were called neural networks, to rapidly improve things like the ability of an algorithm to sort of label an image correctly from a collection of images. Specifically, as you can see here, this is what's called the Imagenet challenge, where the kind of crowdsourced from people around the world. And there was a shift that started around in 2009, kept on going. By 2013, the computer was about at 85%. This is a task that human beings perform about 95%. But then only 5 years ago, so this is not long ago, the computers got better than the humans at labeling images that are drawn from the internet, from a collection of images. And the question is, okay, here I've shown you can do it for text. Here we can do it for images. We know this is also going into autonomous vehicles. What's really going on? So we have this expanded ability to predict things using data, to predict the next move, to predict what we're looking at, to predict what people might say or do in a particular situation. And so along with my colleagues, Rebecca Henderson and Ian Coburn, we kind of tried to think about what is the nature of a technology? How is AI different in terms of it being a new type of innovation? And specifically, even relative to previous improvements in areas like robotics or algorithms, what we realized was this shift that we've been seeing since the early 2000s has sort of two interacting qualities. The first is that this ability to predict things is very general purpose. These neural networks, these machine learning algorithms, can be applied across wide varieties of prediction problems, ranging from emergency response to writing articles for the newspaper, to predicting which businesses might be successful or not, to predicting whether or not a person who has at a particular level of COVID is going to get worse or better, as my colleague Dina Katabi here at MIT has done extraordinary work on. But even more so, okay, so this is a very general purpose technology, and that can be applied to lots of things. Right? We already use AI, and also, when we search Google or when we are on Facebook with the algorithms that serve us ads and so on and so forth. But as well, the ability to predict the outcome of experiments, which is what an AI can do, is itself an invention in the method of invention. It helps us not only predict things that we already kind of are doing on a day-to-day basis, but it helps us itself in the innovation process. Rather than have to test 1,000 drugs before we put one into clinical trials, it can dramatically reduce the amount of early work we do with the drug, and therefore allow us to optimize the process of bringing drugs to market across a wide variety of domains. In other words, artificial intelligence may represent a new general purpose invention for the method of invention. Just to be clear, I'm going to sort of show you a little bit how fast that shift has occurred, and kind of within the context of the development of the kind of, here we have the founding fathers of AI. I think we can agree that the 1956 Dartmouth Conference was not exactly the most inclusive group. It was all white men from the United States. Even leading computer scientists such as Grace Hopper were not invited to this meeting, and that's had consequences to this day. But this, starting in 1956, the field of artificial intelligence really broke into three broad domains: symbolic systems, robotics, and neural networks. And interestingly, for the first 45 years, it was the work in symbolic systems and robotics that were the most academically prestigious. That was where a lot of the attention went, where a lot of the money went. But then, as I said, there were some breakthroughs starting in the early 2000s, kind of picking up on some of the work that actually had been done in the 1980s, that led to this new potential, particularly for the world of neural networks and machine learning. Specifically, what we see is, starting in the early 2000s, a dramatic increase in the rate of learning, in the rate of publication in the learning domain, in this neural networks, machine learning domain. And specifically, starting in 2009, we see a dramatic rise in not computer scientists writing papers for themselves in journals that, to be honest, very few of us could read or maybe even understand, but we see a dramatic rise in actually the use of AI in domains outside of computer science, in domains outside of computation. So the applying that computational tool to agriculture or drug discovery or architecture or whatever it might be. So for example, here's just one example that I find just fascinating. In Dubai, they are building one of the most ambitious new museums in the world. And the architectural firm, a very prestigious architectural firm, I believe from Germany, might be from Austria, Buro Happold, from Northern Europe, Buro Happold, they are very explicit that the very structure of this new type of museum of the future uses shapes and geometry and architecture that literally would not be feasible or be able to be conceptualized without the advanced machine learning in structural materials that's enabled this kind of unique shape, structure, and design. So in other words, what we see here is that artificial intelligence is not simply the application of technology. It's not just going to give us an autonomous vehicle and that's all, and then we'll just that'll be the end. It's changing how we solve problems and develop innovation across multiple fields. So, what are the implications of this AI shift for Korean innovation policy and strategy? The first piece of news is actually rather positive, which is that, interestingly, if this is, for example, looking at patented inventions, this is an area where China has made a very sizable investment. I think many of you in this audience will know that. The United States is sort of distant but very strong second. But then the two other countries that kind of are in the game in terms of inventive activities, both papers, publications, outputs of various types in artificial intelligence are Japan, and just behind that, South Korea. Interestingly, this is a very, remains a very concentrated, geographically concentrated domain. So for example, most of Europe is applying AI for business problems, but they're not doing that more, they're less involved in the more fundamental innovations that are themselves reshaping that process of innovation. And I think many of you might have even been involved with this, might have already commented on it. It is not surprising. Korea usually has a strategy for many things related to technology and innovation. And there is an integrated government strategy here that really talks about, towards AI, a world leader beyond IT, AI for everyone, AI of everything. So I think that's a very promising start. But I want to kind of suggest that if you look through this strategy, it really focuses on how primarily to apply AI to domains that are already existing. That it's thinking about the near or medium term applications of AI in terms of infrastructure, in terms of social media, in terms of maybe helping us with our health records, so on and so forth. But I would argue that the longer term strategy around AI needs to really grapple with essentially a few key questions. Where is the data for this innovation going to be produced and under what rules? Who and where will the innovations be produced? And ultimately, how are we going to shape our AIs to ensure that the benefit from that innovation achieves economic development, inclusive economic development, and inclusive social progress? I want to sort of end, I know I'm already running a little bit out of time, with a little bit of a story about an earlier era of a dramatic shift that really has transformed ourselves. And so this over here is actually the wind tunnel that was originally produced by Orville and Wilbur Wright. And so the history of that is that ever since the in 1891, with the invention of the internal combustion engine, people knew there was an opportunity to use such engines to create heavier than air flight. The problem was the design of aerodynamics, And it turned out that most people were using data about sort of wing design and things like that, using gliders. It was actually fundamentally flawed. In fact, we know it was so flawed, the man who produced it, Lilienthaler, actually died in an accident on his glider. His glider didn't work, but everyone was using his data. And interestingly, it was when Orville and Wilbur Wright went back to their home in Ohio after a very disappointing time out at Kitty Hawk, and they were able to run more than 100 experiments over the course of a winter, so that that allowed them to iterate the design that allowed them very quickly, using that data, to transform into heavier than air flight, this famous photograph. And interestingly, the interesting part of that, though, is that while they could predict that they could produce a machine that could fly, the Wright brothers and even the people of that era were actually relatively unable, they were not very good at ultimately predicting the impact that the invention of flight would have on the human experience. Thank you so much. I look forward to the comments and questions with Sung-Wook. And thank you once again. I'm looking forward to this, I hope, for a very interesting conference.
For your insightful presentation and suggestions. I have already one question from the floor. So the first question I have is, how can deep learning help academic research given this black box nature? In particular, in what ways the traditional deductive nature of academic research, such as hypothesis testing via econometrics, can be helped by deep learning?
Yep. So I actually, I'm going to give I could give a very long answer to that, but I know that we have only a brief amount of time, and so I'll try to package as much as I can in, and if the person, I could be happy to take questions more offline. So I would highlight three different insights. The first, and perhaps most important, is that for economics research or social science research, we can use AI to uncover. AI is very good at uncovering structure in data that may not have been obvious in advance. And to be clear, if you just go do that, and we've had many students, who fall into this trap, you could of course just go down that and you end up with no hypothesis, no structure to your argument, so on and so forth. But for example, in a project that Sung-Wook is aware of, the Startup Cartography Project, we were actually able to use fairly advanced machine learning at the time, this was about 7 years ago, to actually characterize at an early stage whether or not individual companies were likely to be successful or not in terms of having very strong growth outcomes. Think of big IPO or acquisition. We did, right? Now, once we did the machine learning, we then actually were able to reduce the complexity of that model by orders of magnitude, and actually all the results that we've ever published have actually been used just straight logit, just a very simple, with some interaction effects. So what AI can do is help you identify places in the distribution of outcomes where subtle interaction effects might occur, which you then can pull out and then think about undertaking more traditional economics research. If I had to recommend, there are a number of great people that are working on the integration of AI into more traditional economics and social science research. I will just call out Sendhil Mohathan. I'm at the University of Chicago, but even my favorite is perhaps some of the, and she has some great lectures online, is Susan Athey at Stanford, who's really been at the forefront for now almost a decade of really combining artificial intelligence and causal inference. And she has a wide variety of collaborators with her in that effort, including, as some of you know, our most recent Nobel laureate, Hito Imbitz. So I hope I didn't throw too much in there, Sung-Wook.
Okay, thank you. The next question is, the current status of machine learning is data-driven machine learning, which means the ownership of data itself is very, very important. And in some cases, it can be used as a source of market power. So your grand suggestion, depending on machine learning as a new kind of GPT, so how can you address that kind of blocking access to the large pool of data set just they own the data itself. So what kind of grand scheme we need to prepare for the future?
Thank you, Sung-Wook. Exactly. So first, that's an excellent question, and one that Rebecca and Ian and I have sort of written about a little bit. Let me make two comments there. First, I would say it's not just market power, it's also state power. I mean, interestingly, many of the advances that we're seeing in China are because the state itself is enabling individual preferred companies to get access to the best data sets using some of the tools of surveillance, and that itself is giving them an advantage in their ability to do prediction, not just in China, but in other markets around the world. And that's not, once again, there's many things that, so I just would note that there's an important kind of concentrating role as well in some government contexts as well. Vis-a-vis, in terms of the direct question of market power and data monopolies, my suggestion would be that vigorous policy to unlock data, to make data, to make the insights from algorithms transparent. So in other words, just like I talked about before, where you can use the AI, very complicated model, but then build a very intuitive model that people can understand, and the data behind that should be made accessible. And to be honest, my view a little bit is that it's important enough because it is an input into the rest of the innovation process that we would benefit from proactive government policy that makes it within leading tech firms' interests to create these sandboxes, these pools of open data, given the enormous data at their disposal. I'm not sure that I would mandate it, but I think I might provide very strong and very meaningful incentive to do so.
Well, thank you very much. So I think this is time is running out, so it is good point to I introduce our second keynote speech today. Thank you very much, Scott.
Thank you so much.
Thank you. Okay. And it is my honor to introduce our second speaker, Professor Benjamin Jones, Gordon and Lula Gund Family Professor of Entrepreneurship and Professor of Strategy at the Kellogg School of Management, Northwestern University. Ben explores the source of economic growth with focus on innovation, entrepreneurship, and scientific progress. He also studies global economic development with focus on the role of education, climate, and national leadership. Ben served as a senior economist for macroeconomics for the White House Council of Economy Advisors in 2010. His creative approach to important questions have fascinated researchers and policymakers. Personally, his insightful advice helped me through my PhD training. Ben did his bachelor's degree in aerospace engineering at Princeton University and did his PhD in economics at MIT. The title of his speech is Leveraging AI to Accelerate Innovation and Scientific Progress. Please give Professor Ben Jones a round of welcome applause.
Well, thank you, Sung-Wook. It's great to see you, albeit virtually. It's great to be with everyone here. It's great to have a chance to talk about these subjects. Great to listen to Scott Stern as well. So I'm sharing my screen. Can you just make sure that you can tell me that you can hear me and see me? It looks like you can. Okay. I wanted to talk about AI in the process of innovation and scientific progress, building quite a lot on what Scott was saying and being, I think, quite complementary to what Scott was saying. And I'll also make some more general comments towards the end here. Okay, so when you're thinking about innovation, scientific progress, in many ways, you can think of it as a problem of creative search, right? There are many things you could study in any domain, and you have to pick what to do. You have to pick a door that you're going to go through and discover what's behind it. And of course, we don't know what's behind those doors to start. We have a guess of what might be some good doors to go through, but we're not sure, because innovation and scientific progress is fundamentally a step into the unknown. It's a step into doing things that has not been done before, and so it's a high risk and highly uncertain endeavor. And of course, we collectively, as a society, as a globe, as a Korean nation, as the United States, we only have so many people who are research and development R&D workers, scientists and innovators, and you can't go through every door. So you really have to make some choices. And what I want to think about today primarily is how AI can help us in that creative exploration process. And to give you an example, let's just start with the genome, the human genome. So there seem to be about 20,000 human genes, give or take, in the genome, and far more proteins that these genes, because one gene codes for multiple proteins, and so there are many, many, many more proteins even than that. But most of the genes in the genome are not being studied. There's a huge biomedicine apparatus in the world, but people are focused on only a subset of those genes, ones where we think there may be a protein or a process that's relevant to a particular disease or something else, and much of the genome basically remains unexplored. So in some basic sense, the reason I give you this example is because, in a sense, the human genome is a defined search space, right? If I said there are open questions in cosmology or in electrical engineering, sure there are, but it's hard to count them. But with the genome, you can sort of say, okay, well, there are 20,000 genes that we don't understand, and so they're a very concrete and finite but large set of doorways that we might go through. Now, when you add artificial intelligence into the creative search process, let me start with the most ambitious idea, which is we could think of artificial intelligence as adding more humans into the R&D process. They're like additional workers. Of course, here I'm thinking more about artificial general intelligence, right? So if we're ever to create a low enough cost we have to create an artificial general intelligence and have it be low cost. Then we can, of course, if this is sort of person is as smart or smarter than the average R&D worker in some sense, and has the necessary skills to do research and development work, then you can make many of these low-cost artificial general intelligences. And in a way that would be a potentially fundamental shift in the history of humanity and innovation, because instead of having to pick which doors we go through, we could start going through a lot more doors simultaneously. And the reason is, we only have so many people, and we have to kind of, grow the population, train a lot of people. But if you can do if you can make a low-cost brain equivalent, and put it in capital and physical capital, then that will scale naturally, and you can make a lot of it. And so, the more we make, the more we discover, the more we grow, the more resources we have, the more of these AIs we can make. And that kind of virtuous feedback loop, maybe it's not virtuous, but that positive feedback loop, you can actually get a growth singularity out of that kind of process, as I've discussed with Philippe Aghion and Chad Jones in some prior work. But this all seems very far away. I don't think we're that close to artificial and general intelligence. And so this is not how we're going to be using AI in the near term. We're going to do a lot of what Scott was talking about, which is using AI as a tool. And in particular, I have a similar, apparently, diagram of a machine learning algorithm where we have kind of a lot of data going in on the green, going through various layers of statistical processing, and then producing the best fit to a series of outcomes. And this kind of machine learning process, or deep learning, or other forms, they're not really replacing humans, but they can certainly assist humans. And I want to kind of drill down on that with some examples. And in the R&D context, I think they're particularly useful tools because they're good at prediction. They're good at categorization. They're good at prediction. There's also reinforcement strategies. But I want to emphasize prediction. In fact, the prediction machines angle that Scott was also gravitating towards in his talk. And the reason I want to do that is because I think that's directly relevant to the creative search process and helping us make the choices. All right. So in other words, if this is the scientist wondering what door to go through, basically these current, available machine learning algorithms can really help you choose the door, right? It won't give you certainty about which door to go through, but they can help you find doors with much higher probabilities of delivering real value. And of course, they can do that very rapidly. In some sense, they can begin to help you try a lot of those doors yourself. All right, so what you can think of the current AI, machine learning in particular, is helping you find the door that is best to try. And so that could also, of course, accelerate our innovation process in any number of domains. So just to give you a few examples of that, so here's a paper from 2018 in Nature looking at chemical synthesis. And figuring out how to synthesize organic molecules is really very difficult. And failure in finding a pathway to synthesis is quite common. So for example, you tend to have some target molecule, organic molecule you want to make, and you have to figure out kind of what the constituents, smaller molecules you'll start with that you can get, and then what reactions you put them in what order, and what combinations to kind of create a cost-effective or even possible synthesis pathway. And so this is kind of the art of chemical synthesis. And what Segler et al. Do in this Nature paper is they use a deep learning algorithm trained on virtually all organic reactions that have ever been published to then predict optimistic pathways that you could try experimentally. And it turns out that with this algorithm, you can solve for twice as many molecules and providing a synthesis pathway as was possible with prior approaches, right? So rather than the chemist trying through, their own intuition and wisdom, trying to figure out which doorway to go through to synthesize a chemical, this can often give you much better guidance, not perfect guidance, but can help you pick which door to try or doors to try. And that, of course, will elevate the efficiency of research and success in producing new chemicals and new manufacturing processes for chemicals. Another version is a protein structure. So here's a 2020 paper from Senior et al. This is a AlphaFold. The protein structure, the gene codes for the protein structure is essential to its function. But determining the structure is actually very difficult. It has to be done experimentally in structural biology. So there's a typical complex, very large molecule protein that you're trying to figure out the structure of. That's actually the COVID SARS spike protein, that's the sequence done in a lab, not using machine learning, in January of 2020, which led to the targeted mRNA vaccines that in fact recognize that spike protein. So AlphaFold is a new AI tool that says rather than trying to do this by growing crystals in a lab and crystallography, it's an AI tool that just tries to do it from genetic information that's coding for the protein. And it turns out that it can, that it works really very well, especially for proteins that seem very hard to synthesize and test because they're so complex through experimental methods. And of course, you can apply this very quickly across wide ranges of proteins. So it can be both a very strong guide to protein structure, which is incredibly valuable to thinking about function and figuring out disease and points of attack for researchers, and it can also be done at very high scale. All right, so these are potentially big advances that are in fact making researchers, not replacing researchers, but making researchers in these areas figure out which doors to try and much more efficiently, and can really accelerate the progress of knowledge. A final example before I go on is about replication. So here's a recent paper by some colleagues here. It's just has come out in the Proceedings of the National Academy of Sciences. And of course, in science and research, we're always building on what has been found before to direct our creative search. We're trying to figure out what doors to go through based on what we already know, and which tells us something about where we think further progress can be had. But we also know we're kind of troubled by the fact that a lot of scientific studies don't replicate. So we're trying to build on what's already known, but maybe what's already known is wrong. And that would, of course, be very misleading in terms of what direction you go on and build your own research. So, for example, there's been a lot of commentary about the difficulty of replicating so-called landmark studies in cancer, where other labs have trouble finding the same results. It's true in psychology. There's a whole issue of replication problems in the sciences. So in this paper from Yang et al., they basically take deep learning natural language processing algorithms and apply them to the full text of papers in a supervised data set where we know some of these things replicated and some of these papers didn't replicate. And in fact, it turns out that you can predict from the figures in the text of the paper which papers are more likely to replicate. So that gives us kind of a now high scalable quality control potential tool in helping direct future scientific inquiry. Okay, so I mean, those are just some examples where we're using deep learning to help us make choices in the directions of research that we try. But of course, the problem of making choices is not one just in creative search. It's also in many other things we do and are trying to optimize in our daily lives as businesses. You know, in a health context, not just where would I find a new kind of approach or treatment, but what's the diagnosis of this patient? Of course, radiology and reading scans can be, AI can be very good for that in its categorization capacities, in the same way that it can recognize cats on the internet and other photos. What is an appropriate treatment plan given a complex set of factors for a given patient, genetic or behavioral or experiential or otherwise? And then very broadly, you know, what kind of investment would you try? Let's get away from health. What would be your investment in the financial market, or where should I locate a hotel, or, you know, where should I be investing in general? Those are, of course, all choices where you have a limited set of resources and you have to deploy them in some specific point. So you would imagine that prediction algorithms could help you in all of those contexts. So I mean, I think this is an incredibly powerful tool, but I also want to close with a note of caution, my last set of comments, that, you know, of course, machine learning is a great tool, but it also has limits. And can we characterize what those limits are? I think we can have kind of a rules of thumb, you know, for when we think machine learning might work well and when it might be more limited in its capacity to create advance. And, you know, one thing to just remember is that machine learning in some sense might work best when the environment is constant, in the sense that the rules aren't changing. And the reason is because it's fundamentally machine learning algorithms are just prediction machines based on the data that they see. So they see what we know, or what the way things have been, and they make predictions and optimize based on that. But if the world is in some sense changing, so for example, if the world is evolving because technology is evolving, or policies are evolving, or market structure is evolving, you know, and agents are making evolving choices in this evolving world, then these sort of historically based predictions may become incorrect as the world has moved on. And so you could beat the ML, the machine learning algorithm, because you have better knowledge of the world, and it could in fact become misleading. So you have to beware sort of non-constant environments where there's adaptive responses in the environment. And of course, social science systems and business systems, our systems and international systems, our systems of humans, are systems of adaptive and strategic response. And so we have to be a little careful about this sort of prediction based on a fixed data set or fixed experience. Now, this issue is quite general. In economics, we often talk about it as the Lucas critique from well before AI, which is just the Bob Lucas, the Nobel Prize winning macroeconomist, pointing out that, you know, if you try to base everything on prediction, it can be very, very misleading because when policies change, behavior will change, and what happened in the past may not happen again in the future. And that's why, in some sense, a model, and if you can come up with an actual model of reality, that might actually beat a simple prediction, no matter how sophisticated that prediction system is, because the system is trapped in its environment and what it's actually seen. But a model can extrapolate, potentially, if it's the correct model or approximately correct model, beyond the environment that you have seen. In biology, this is sometimes called the Red Queen hypothesis, and that's the idea that in evolutionary biology, every species is reacting to every other species, and there's kind of it's a nonstop horse race of evolution. So the environment is kind of constantly changing, and extinction events happen when you no longer have fitness between your species and the environment. And so, you know, that's not true. You were very fit to your environment in the past, but in the future you're not. The environment changed on you. That's a very similar kind of issue in a biological context. And more generally, we just think of agents acting in some kind of equilibrium behavior. So again, if you have some model of how the equilibrium emerges, that may be a far more powerful predictive tool than machine learning. Machine learning is great when you don't really have a theory, because it's very complex and you don't know. So you can just throw a lot of data at it and it can make great predictions. But let me give you just a counterexample. So for example, if you were to get on a plane, you know, if you were to buy a plane ticket, you typically find that, you know, certain times of day, the prices are really high to get the plane ticket, and the planes tend to be full. But also, like maybe around 2 p.m. in the day or very late at night, the plane tickets are kind of low relatively on that route, and the plane isn't full, right? So if you just gave that to a prediction algorithm, it's going to say, aha, if you want to fill your planes, raise the prices. It's going to say, charge high prices, that's when planes are full. But of course, that's ridiculous. Any economist or any person on the street will tell you, no, prices are high because demand is high. And so that's why the plane is full, and then they're able to charge high prices. But again, that's a model. It's a very simple model that tells you there's supply and demand, but a machine learning doesn't have that model, or, you know, so it's going to just predict. based on what it sees. And so it can be misleading because of equilibrium behavior. So, and if you have a simple model, that can be very, very powerful. Anyway, so machine learning makes predictions based on past experience, and if the world is changing, it's misleading. But when I come back to innovation, my last point, what's interesting about sort of discovering what's new, like, what does a protein do? What does a gene do? Can I read this scan? The tumor is not going to react to the fact that you figured it out. What a gene does in the human body we haven't discovered it yet, but it's not going to change what it does because now we know what it does, right? So those are not social science systems where they're strategic agents that are evolving and responding to changing information sets. So in some sense, discovery is a great place for machine learning because at some level, nature is constant, right? Whereas, looking at sort of where to put your hotel is a complicated thing because people are going to be reacting, or should I buy this investment in finance? Well, if everyone does that, machine learning says do that, but then everyone does it and that's no longer the right investment, or something else becomes a better investment. In those systems, it's more complicated to apply. Okay, so those are my comments, and I hope that you find that useful. I'm happy to take any questions.
Thank you very much, Ben. So it was fantastic topic. So I have already a couple of questions from the floor. So the first question I got for you is, do you have any view as to how to increase AI-related interdisciplinary research across academic disciplines? And that was the first question. The second question, related one, was, do you think the world among them are being destroyed? So any implications for Korea and other countries? That is the second question.
Seung-wook, let me try to answer the first question, and then maybe you can ask me the second question again because I'm not quite sure I understood it. So the first question is about interdisciplinarity. I just didn't hear it quite correctly. The first question is about using AI in an interdisciplinary context, and I guess what I would say to that is great, and use teamwork, use collaboration. So I think to some extent everyone can learn about machine learning, especially if you have a background in statistics, because it's not that complex to understand what you're doing. But I think in terms of applying the best methods in the particular circumstance, there's a lot of knowledge that's developing among true AI specialists, from natural language processing to visual processing to other methods. And so rather than try to be that person yourself, you want to find and work with people who have those skills. And what they can bring to the table is sort of a capacity to apply the most appropriate cutting edge AI algorithms and deep learning or some other method to the problem. But what you bring to the table is the question that, the application. So if you understand what AI can do, like prediction, you can be thinking about, okay, well, where can I do that in this disciplinary context? And then you can team up with AI experts. So to the extent that that's what you mean by interdisciplinarity, I think that's a great way to go, and I would again use simple answer: collaboration of specialists to attack the problem you have in mind. Now, in Seung-wook, can you ask me that second question again, please?
Yeah. So the second question was: do you think the walls among them, the walls between academic discipline, can be destroyed by AI?
Yes. I don't think so. I think AI is a tool. I don't, in the sense that I think we should try to overcome those walls, but I think again it's probably through collaboration, because not surprisingly, perhaps from my own orientation of my research, I think that to do truly frontier work in deep areas of knowledge, which would include biotechnology and engineering and nuclear fusion and all these things, you really need to be a deep domain expert, and nobody can know everything. So you want to team up. And I think to some extent, walls are inevitable in the sense that, you just don't know it's very hard for someone who is an economist to say something meaningful about how to do magnets in a nuclear fusion torus. And it's somewhat very difficult for someone who knows how to do that to say something very useful about monetary policy and macroeconomics. Because by nature, we're going to specialize in that expertise is always limited. So I think those are walls, but I would think let's connect and let's bridge those walls through collaborations. And I think AI sort of breaks down the wall. I sort of think of AI as a very general purpose tool along the line Scott Stern was saying, that works in many disciplines, rather than necessarily crossing, helping you cross disciplines. But I haven't thought about the question very much, and I think it's a very interesting question.
Okay, thank you. And we have questions from the floor. Professor Lee In-bok actually raised his hand to have opportunity for question. Professor Lee, can you please proceed?
Okay, thank you. It seems like my ability to turn on the video is somehow restricted now, so I'll just go by my voice. So I think partially you answered some of my questions for the first one, so let me move to the other one, which is about sort of academic norms. So when we think about, say, experiments these days, we see a lot of new kind of norms or expectations being imposed with, say, pre-analysis plan with the replication crisis. So, we're trying to tie our hands about in a way, sort of finding new questions in some extent, right? So we want to set out the expectations ex ante and try to go through the actual test and so on. Mm-hmm. How do you think, in light of that, for machine learning to be applied to general social sciences, academic norms should or would evolve in the future?
So I think that, like the replication crisis, I guess I would, as you suggest, can be combated through replication, obviously, but also through avoiding bad statistics and the tendency for people to keep, data mining their own small n data sets. If you have a small n data set and you try too many things in it, you're going to find stuff that isn't actually there in terms of statistical significance. So I think there's a whole bunch of processes that don't necessarily have much to do with AI, but are, I think psychology, for example, as a field is making a lot of progress against their problem with replication by increasing the sample size, and then pre-registry is a great idea. We see that in economics too. And it's interesting. I mean, I think, one of the funny things about digitization and empirically is that we have such huge data sets that, often with ML, you're going to be using an absolutely enormous data set, but anything you're doing, even descriptively, of any kind of econometrics, in data sets with millions of observations, you're not going to really be worried about finding something that's not there because your t-stats are going to be huge. I mean, the patterns are going to strike you. And if you have 10 million observations and your t-stat is 1.96, then you have a problem. It should be 100 times that if the effect is really there. So in some ways, I feel like digitization, which is sort of going on separately and enabling AI, is also enabling us to avoid p-hacking or replication issues in these large data sets. I think where it's more challenging is in the sort of continuing field experiment world, right, where it's hard to run the experiment every observation you collect. And this is true in a wet lab when you're doing something. It's true in a drug trial. It's true in a social science study in the field where often your observation counts are low. That's where these sort of important norms around pre-registering your study and are really important. And I think when you look at the replication crisis, whether it's cancer findings or it's psychology, those are usually small n studies, small observation studies, and that's where they get into problems. And so we need norms that are really targeted at those types of studies. Was that a constructive answer?
If I could just two-finger on my own question.
Yeah.
And push back just a little bit. I mean, on the one hand, is the issue definitely about p-hacking small n or increasing sample size, but it also has to do with, I think, the kind of traditional expectation in social sciences where you start with a clearly set out theory and hypothesis, and you're going through the test by collecting the data on the one hand, versus, I think, still, not all, but quite a lot of research stemming from or using the tools of AI or machine learning also have a greater tendency to be at least a little more descriptive or exploratory, and from there generating new expectations. And you, I think, also suggested a few of those during your presentations about sort of discovering new questions. How do we reconcile between these two? I think this is, I guess, a little more of a bigger, almost like ontological question for social sciences, but can we actually target those goals of doing better, rigorous social science on the one hand, while at the same time leveraging all the power that may be given to us by using bigger data and better methods?
So one other comment. I mean, I think when economists first heard about machine learning, their instinct was that's data mining, And that's bad because you're going to find fit of things that is not there. And that the results are spurious because because to your point, you don't actually come with a formal hypothesis. And so there's a real risk of just finding stuff that happened to be there because you looked so many times and ran so many models. However, what's sort of mysterious about machine learning in general, and not just deep learning, but is the use of these folds, like this way of sampling. And I think computer scientists so economists wouldn't even try it because they were convinced about that it would be data mining, and maybe computer scientists weren't really aware of that issue. And so they just kind of held data back and they would randomly sample subsets and then fit it as best they could. And it sort of turns out heuristically, not according to any asymptotic econometric theorem I know of, but heuristically, that actually works and has very good out of sample properties, and it turns out not to overfit the data. So I think built into machine learning is a process that is sort of mysterious why it works, but avoids that kind of overfitting. So I think it is exploratory and descriptive in that sense, but it probably doesn't have that spuriousness feeling, and that's sort of why it actually works at all these things. Like it really does find cats on the internet because it wasn't overfit. It's just very good at it. So in some sense, I guess I'm less worried about that in the sort of fitting sense, but in the sense that an algorithm that fits something that you don't really understand how it fits something, and isn't based on a particular theory, I agree. I mean, there's some view that machine learning is a bit of a dead end because it doesn't reveal. It's a tool, but not a truth revealer. It doesn't reveal. It can reveal truth in application, but it doesn't actually tell you why it works. And I think there are a lot of people working on more interpretable versions of machine learning algorithms so that it can tell you a bit about what's actually happening and sort of guide your theory development. But that's in the sense where what I was saying before about, ML is really good when you don't have a theory and the system is very complex, and that really is very complex. But if it actually is a reducible system, and this not reducible, maybe not the right word, but in the sense that there is a theory you can bring with not too many equations or functional forms that in fact really is correct and it kind of gets the data, I think that's going to tend to really beat a machine learning algorithm, actually even in prediction and out of sample prediction, and then it's even going, but of course it's also going to tell you sort of why it works, and from that I think much more good things can flow rather than kind of a blind tool that we don't fully understand.
Thank you very much.
Okay, thank you. So I think this should be the last question. Actually, for my question to Ben. So from my personal experience, the evaluation of scientific program and project in the age of specialization become really, really complicated. So is there some guiding principle from your side that we should evaluate a scientific program, and then the key important we need to identify or check for the efficient and effective scientific program? And the second question is, when we design the reward system based on that assessment, especially among very different scientific disciplines, there are big conflict for the financial resources. But in that case, how can we set priority among different set of scientific disciplines project? Any broad suggestion or guiding principle?
That is a fantastic question. It's a huge question. I feel like we could have a multi-day conference trying to answer that question. Let me try to give you a short answer. I know my answers have been a bit long-winded so far, but number one, there are lots of metrics you can use. So you can think about how scientific insights are built on by other science. So it's citations received, how they're built on outside of their field. But you can also look at how science is built upon by policymakers, or by patents, or in drug development, or in products that are introduced. I think digitization and the new data sets that we have are allowing people to connect sort of public uses of science and research in new and complex ways that allow us to see how science is felt broadly in society. And I think using those kinds of big data tools and measures, one can get a sense of how valuable the work is. But my second comment and final comment on this question is that, we think things are very complementary. So I would be very careful to say we should bet on this. And like we should only bet on applied research or only bet on basic research, or we should only bet in this area of research, like electrical engineering or something. And the reason is that, you know, the spillovers we see from one area to another are very high. Like, so, you know, mathematics papers don't usually get built on very directly in patents, but they get built on by computer science papers that get built on in patents. And so, you know, some of the mathematic insights are some of the most fundamental and used so broadly. So you have to be very careful about dismissing certain kinds of research because you don't see an immediacy potentially in its application. And so what I would really recommend, if I give you a recommendation, is bet widely, but make a portfolio. And you know, partly because we don't know what's going to really work out, and nobody does, and many things interact. So I would be betting quite widely. I'd be betting on diverse forms of human capital, so you can bet widely, and your innovation system isn't a monoculture, but is a very diverse. You know, there's AI, there's you know, that's only one of many poles of action, because there's so many other areas of science and engineering and technology that can have huge implications in ways that you just can't anticipate. Again, if we could anticipate it, we wouldn't need to do it. The whole point of R&D is that we're stepping into the unknown. So don't believe people who have very strong ideas about you got to invest in X. And I would just suggest develop your human capital in a diverse way and make a wide portfolio of bets.
Okay, thank you so much. So since it's time to wrap up our wonderful keynote speech session today, again, I really appreciate your insightful presentation for both Scott and Ben. Thank you so much.
Thank you.